Which celestial body is breathing in the icy space? 3I, Atlas, a traveler from another star system, releasing 40 kilos of water every second into the freezing vacuum, too cold for the sun to cause this activity, causing astronomers to whisper that it is acting like a living organism. But the story of this comet star does not end there. It also carries mysteries like Nico, strange, not accompanied by cyanide iron in its tail, along with whispers about origins dating back billions of years, older than even our solar system meanwhile, far from this star visitor. Citizen scientists accidentally discovered strange circles, the largest radio circles ever recorded, aligned with Mercury and Ceres, aligned with a curious moment in the October sky raising questions about a possible connection with BAE Atlas, and Blue Origin's October flight raised more questions than answers, even whether it really happened or not. Let's explore to the very end, as we face these thought-provoking questions in our new multi-topic broadcast aimed at helping night owls stay updated with all the cosmic news unfolding above the sky. If these mysteries have captivated you as they have me, be sure to like and subscribe so you don't miss any updates. As these events unfold in real time, leave a comment to let me know where you are watching from, what time it is there, and whether you believe we are getting the full truth about these world-changing discoveries. And if you want to help this community grow, please share this video on X, Facebook, Reddit, or even just in your chat groups. You are the reason we can continue to pursue stories like this, so thank you for supporting us. Part 1. Impossible Signal. Imagine this. You are drifting in the cold silence of space, more than 30 times farther from the sun than Earth, where sunlight is just a whisper. Frozen, solid, the comet star falls into hibernation. Everything is deep asleep, and then you see it, a comet, violently pouring water into the void, ejecting 40 kilos of this liquid into space every second, not a small drop, but a flood gushing from a frozen rock, where water should not flow. This is BAI Atlas, a comet star that has come to our solar system from somewhere else, carrying rules from the backyard of another star. And those rules do not match ours at all. The first sign came from Swift, a space telescope designed to hunt gamma-ray bursts. Swift turned its ultraviolet eyes towards BAI Atlas in early 2025 and discovered the impossible. A halo of hydroxyl molecules surrounding the comet. Hydroxyl, or OH, is what you get when sunlight tears apart water molecules. It is the echo of dying water, and when you see OH, you know water was just there. And Swift saw many truly astonishing numbers at a distance of 3.51 astronomical units from the sun. BAI Atlas is releasing 1.3510 to the power of 27 water molecules every second, equivalent to 40 kilos per second, to put it simply. This is like pouring the amount of water in a small car into space every minute, at a distance where our comets are almost completely silent. Comets in our solar system do not do this. So far from the sun, they are cold, hibernating, almost dead. Ice needs heat to sublime, to change directly from solid to gas, without melting, and there is not enough solar energy at this distance to drive that kind of activity. Our comets wait until they are much closer to the sun to wake up and start spewing gas and dust into space. But BAI Atlas did not get that memo, you may recall. Oumuamua, the first confirmed interstellar visitor, that object was bone dry. No water, no outgassing, just a tumbling rock, accelerating through our silent neighborhood. Then comes T. Borisov, the second interstellar comet. The body is definitely active, but it behaves exactly like our comets. It follows a predictable script, and it is boring in the best possible way. Unlike both those objects, it is alive in a way it shouldn't be. It is screaming water into space, where there should be silence and a question hanging overhead. Every astronomer has pointed their telescopes at this object very simply. How, what mechanism can drive this? Could it be some strange ice? Sublimating at temperatures we thought were too cold. Is the interior of the comet still warm from its birth, billions of years ago? Is it spinning in a strange way, focusing sunlight onto reservoirs of material, volatile, hidden, or is there some chemical reaction happening inside the rock that we have never encountered? Water is just the beginning. 2I/Atlas is also leaking other things: cyanide, nickel, carbon dioxide in unreasonable concentrations. Each new observation adds a layer of mystery. Each spectral line appearing in the data is another question mark. This is not just a comet acting strangely, this is a comet, seemingly operating under a completely different set of physical rules, rules written in another star system under different conditions, with different chemistry, and now it is here in our solar system, giving us a front row seat to witness processes we have never seen before. What keeps astronomers awake at night is this. If 2I Atlas is doing things our comets cannot do, what does that say about where it came from? What star system builds comets like this? What were the conditions in that protoplanetary disk billions of years ago? And the most thought-provoking question is whether this comet is simply strange, or it is a messenger bringing news of the universe's diversity. Every telescope that can see this object is now pointed at it, including spectroscopy, certainly optical polarimetry, every tool we have. Because 2I Atlas is not just a curiosity, it is a window, a crack in our understanding, and through that crack, we can glimpse something extraordinary. Part 2. Nico. No iron. Comets are thought to follow certain patterns when they get hot enough. Metals begin to sublimate from their surfaces and iron and nickel appear together, like old friends always going together. You see one, you see the other. That is one of the cosmic number lines we have relied on. Except 2I Atlas did not read the textbook. A very large telescope in Chile pointed its spectrometer at 2I Atlas and found an absurd thing that the emission lines, nickel is blazing strongly in the spectrum, unmistakable, impossible to ignore. While iron is either absent or so weak it is barely detected. Nickel without iron. This is like finding smoke without fire. This is like finding footprints without feet in our solar system. This does not happen when a comet heats enough to release metals. Iron and nickel appear in predictable ratios because they are locked tightly together in the same structure. Minerals, they form together in similar processes. They sublimate at similar temperatures. They bond chemically in ways that keep them together. But 2I Atlas seems to have formed in a place following different rules about 2.8 astronomical units from the Sun. Astronomers measured nickel streaming from the comet at about 5 grams per second. 5 grams doesn't sound like much until you realize it is happening continuously, second after second, and iron is nowhere to be found. This is not a glitch. This is a pattern. This comet is telling us something fundamental about its composition. Some explanations have been proposed and none are simple. The first possibility is chemical segregation, perhaps in the environment where BAY Atlas formed. Nickel was incorporated into volatile, easily evaporated compounds, while iron was locked into refractory minerals requiring much higher temperatures to vaporize. Imagine nickel traveling with volatile ices, while iron remains trapped in rocky grains. This could create the separation we are seeing. Another idea involves metal organic compounds. On Earth, we have molecules like nickel carbonyl, where nickel atoms bond with carbon monoxide, and these compounds are volatile. They evaporate at relatively low temperatures if BA Atlas formed in an environment rich in carbon monoxide and other organics. Perhaps nickel was trapped in these molecules when sunlight shone on them. They decomposed, releasing atomic nickel into the comet's coma region, while iron remained locked in solid grains. Then space weathering occurred. Cosmic rays and ultraviolet radiation bombarded intercometary objects for millions or billions of years. Such prolonged assault can alter surface chemistry in strange ways. Perhaps radiation created nickel-rich surface layers while iron was buried or chemically altered. Maybe the nickel we see is a skin, a damaged crust, caused by radiation not reflecting the true bulk composition of the comet. Or perhaps, and this is the most exciting possibility, BAY Atlas formed in a stellar system, with genuinely different elemental ratios. Not all stars have the same chemical composition. Older stars. Stars from different parts of the galaxy. Stars formed from gas clouds enriched by different types of supernovae all have slightly different recipes. Perhaps BA Atlas comes from a place where nickel is more abundant relative to iron. In our neighborhood, perhaps its parent star has an unusual chemical makeup, and that peculiarity is now recorded in every molecule of this comet. But we must be cautious here. Spectroscopy is very challenging detecting emission lines. Faint against a bright background is very complex. There are detection thresholds. Maybe iron is there just below detection limits. Perhaps iron emission is blended with other spectral features. Maybe we are looking at the wrong wavelengths as the comet approaches the sun and heats up. More iron may start to appear. That would be reassuring in a way. It would mean the universe still makes sense. But if that does not happen, what if BAE Atlas goes all the way to perihelion? The closest point to the sun and iron never appears. What if the nickel to iron ratio remains completely inverted compared to everything we have ever seen? That would be revolutionary. That would tell us that planetary systems can produce comets with metal chemistry so different that our models need a complete overhaul. This is why astronomers are obsessively observing BAY Atlas. Every observation is a test, every spectrum an opportunity to confirm our understanding or shatter it. And currently, BA Atlas is breaking more than confirming. Part BA, a comet flips the switch. Comets are thought to brighten as they approach the sun. Very simple physics. More sunlight, more heating, more vaporization, more gas and dust. The relationship should be smooth, predictable, almost boring. BA Atlas seems never to have received that memo. Observers tracking BA Atlas noticed something strange about its color. Initially, the comet looked relatively neutral, perhaps slightly red, typical of distant icy bodies. But as it moved closer to the sun, it began to shift to a vivid blue. Not a subtle change, but a vibrant blue, eerily unmistakable in photos. That blue comes from two sources. Cyanide molecules and atomic nickel both emit strongly in the blue part of the spectrum, and both started increasing sharply as the comet warmed. The brightness increase was not linear. It is not smooth at all. It is superlinear, meaning the emission lines are increasing faster than predicted by simple geometry. When you have the distance to the sun, you get 4 times the sunlight per square meter. That is the inverse square law of basic physics. But the emission from Comet Atlas is increasing even faster. Something is being unlocked. A new process is starting. Astronomers call this phase 6, the phase 6 switch on. Imagine a temperature threshold below which a specific type of ice remains solid, locked in hibernation. Then the comet passes that threshold, and suddenly that type of ice begins sublimating. Gas production soars. New emission lines appear in the spectrum. It's like flipping a switch. One moment the process is off. The next moment it's on. And once it's on, it can run itself if there is enough material to feed it. Comet Atlas seems to have many switches. Water switches on first, as far as 3.5 astronomical units, which is already unusual. Then cyanide and nickel flare up in blue at 6 as the comet warms. Furthermore, each emission shows a different reservoir of volatiles being tapped, a different chemical environment reaching its activation threshold. One model that can explain this involves expanding ice grains in the comet's head, instead of all activity occurring at the nucleus surface. Imagine small ice grains lifted off the nucleus. By escaping gas, these grains drift away from the comet, still cold, still frozen. But as they drift, they are exposed to increasing sunlight. Eventually, each grain reaches its own individual threshold and begins sublimating, creating a dispersed gas source, not just from the nucleus but from a cloud of ice grains surrounding it. This can explain the superlinear brightness increase and the sudden appearance of new emission lines. Another possibility is thermal fracturing. Comets are dirty snowballs, a mixture of ice and rock. When one part heats and expands, while another part remains cold and contracts, stress builds up. Eventually, something cracks. When ice fractures, it can expose fresh material previously insulated. Suddenly, you have new surface area sublimating. New volatiles escape. The comet undergoes an outburst. Comet Atlas may be cracking open as it warms, exposing frozen chemical layers. Then, exotic ices. Water ice sublimates at an ice temperature. Carbon monoxide sublimates at a much lower temperature. Carbon dioxide somewhere in between. If Comet Atlas is layered like an onion with different ices at different depths or in different regions. Then, as it warms, you see a sequence of activations. First, the supervolatiles, then the common volatiles, then, finally, the really stubborn materials, each layer peeling off like chapters in a book. This is not entirely unfamiliar to us. We have seen comets in our solar system do strange things. Some comets have sudden outbursts, brightening by 10 times or more overnight. Some comets break apart as they approach the Sun. Thermal stress overwhelms their structural integrity. Some comets remain dormant until very close perihelion, and then erupt into activity. But Comet Atlas is doing this on a schedule that does not match our experience. It is active at distances where it should be dormant. It is switching on in ways that almost seem intentional. And the stress is increasing as Comet Atlas continues its journey inward. Will more switches turn on? Will we see new emission lines appear, new molecules we did not expect? Will activity stall or will it continue accelerating? Each week brings new data, new surprises. This is not a stable, predictable comet. This is a play unfolding in real time. Part 4. Where does it come from? Every object in space carries a story written in its orbit. Where it is going tells you where it has been. And the orbit of Comet Atlas is telling a story spanning billions of years and thousands of years. Hyperbolic orbit is a technical term for an open curve. A path that does not repeat BAY Atlas comes from interstellar space, orbiting the Sun and will leave again, never returning with an eccentricity greater than 1, meaning this comet is not bound, a free agent, a wanderer. It just passes through. Astronomers have traced its path backwards using recovery images. Recovery is when you search old survey data to find images of an object before any AI knew it. Interestingly, Atlas has been photographed many times by automated surveys, some images dating back when the comet was 6.4 astronomical units away and still approaching, still cold and distant. By stitching these observations together, astronomers have reconstructed its orbit with increasing accuracy, and that orbit just goes outside, returning to the galaxy but not just anywhere. The orbital model, combined with data from the Gaia Space Telescope, which has mapped the position and motion of billions of stars, allows astronomers to make informed guesses about the mysterious origin. Atlas may have, surprisingly, a galactic structure origin. Stars are not randomly distributed. Most stars, including our Sun, live in the thin disk, a relatively flat plane of younger metal-rich stars orbiting the galactic center. But there is also a thick disk, a population of older stars orbiting on more inclined paths, more eccentric than the thin disk stars. These thick disk stars are puffed up vertically, spread further above and below the galactic plane and chemically distinct. They are older, formed earlier in galactic history when fewer heavy elements were around. They have lower metallicity. The orbit of BA Atlas suggests it may come from the thick disk. If that is true, if this comet formed in that ancient population, it could be older than our solar system. Our solar system is 4.6 billion years old. Thick disk stars can be 7 billion years old or more. That means Atlas may carry ice and rock from a time before the Sun even existed. Think about the chemical implications of that. The gas cloud collapsed to form a thick disk star 7 billion years ago, with fewer heavy elements than the cloud that formed our Sun. Supernova explosions enriched the galaxy over time, seeding it with heavier elements than helium. The earliest generations of stars had almost only hydrogen and helium. Generations like our Sun have a few percent of heavy elements mixed in. Thick disk stars are intermediate. They have some heavy elements, but less than us. If Atlas formed in that environment, its composition would reflect that lower metallicity, with less iron, less magnesium, less silicon, all the rock-building elements, but still plenty of volatiles like carbon, nitrogen, oxygen locked in ices and molecules. Perhaps that is why we see such a high carbon dioxide to water ratio on the comet. Perhaps that is why the metallicity ratio looks strange. Maybe this comet is a chemical fossil, from a time when the galaxy was younger and the periodic table less filled. Of course, we cannot be certain. Tracing an object back over billions of years of galactic motion is difficult. Gravitational perturbations from passing stars, interactions with galactic spiral arms, all of that disturbs the trail. But the possibility that BAY Atlas is older than our solar system is extraordinary. We may be looking at a relic, a surviving object, a time capsule from an ancient galaxy. And if we can identify its parent star cluster, a group of stars formed together from the same gas cloud, we may one day identify its siblings, other comets, perhaps even planets, ejected from the same system, now scattered across the galaxy. BAE Atlas may be a letter in a message written across thousands of light years, and we have only just begun to learn how to read it. Part 5. What accompanies it? Comets are not just ice and rock, they are cargo ships, carrying the molecular cargo of the environment where they were born, and Baikal is carrying some very strange cargo. We have talked about water, 40 kilos streaming into space at distances where it logically should not flow. That water, or rather the fragments of Hiroshima left when sunlight tore it apart, is the first clue showing this comet is unusual. But water is only the beginning of the story. Carbon dioxide is the real shock. Observations show Baikal has an extremely high carbon dioxide to water ratio among the comets of our solar system. Water usually dominates. It is the main volatile and the main driver of activity. Carbon dioxide is there, certainly, but only as a supporting player. Baikal reverses that scenario. Some measurements show 95% of volatile emissions are carbon dioxide. With water as the minority component, that is the opposite. That is reversed. That does not match what we see at home. A comet so rich in carbon dioxide. One possibility is the formation temperature, as carbon dioxide condenses at a higher temperature than water ice. If Baikal formed in a warmer region of the protoplanetary disk, closer to its parent star, it may have preferentially incorporated carbon dioxide, while losing some water, or perhaps the radiation environment of another parent star, processed the ice in ways our sun does not, or perhaps giant planets in that system, if present, migrated differently, stirring the disk and mixing material in unexpected ways. Then there is cyanide. Cyanide, or CN, is common in comets. It is the molecule that produces the blue color for many comets, but in Baikal, cyanide appears after water, later in the comet's warming. In our comets, cyanide and water tend to appear simultaneously because they have similar sublimation temperatures. The delayed appearance of cyanide in Baikal suggests it may be isolated differently, perhaps trapped in organic molecules, requiring more energy to break down, perhaps frozen in layers beneath the water ice. And of course there is nickel. Nickel atoms emit blue light, separated from their usual partner iron. We have explored that mystery. But the key point is every element. Every molecule we detect is a clue. Volatiles tell us about temperature and pressure during formation. Refractory materials tell us about condensation sequences and thermal processing. The gas-to-dust ratio tells us about the comet's structure and its fragility. Now, let's talk about the most obvious issue, the panspermia hypothesis. The idea that life, or at least the building blocks of life, can be spread through space on comets and asteroids. Baikal has water, organics, cyanide, important precursors in prebiotic chemistry. If you wanted to design a comet to seed a planet with interesting chemistry, you would include exactly these components. But we must be very clear. This is speculation. There is no evidence that Baikal carries life. No evidence that any comet has ever carried life. The panspermia hypothesis is attractive and plausible in principle, but unproven and has serious problems. Cosmic radiation is brutal over millions of years in intercometary space. High-energy particles break apart complex molecules. Ultraviolet light from stars does the same. DNA, proteins, even simple amino acids can be destroyed. For life to survive a journey on a comet, it would need to be buried deep inside the comet, shielded by meters of ice and rock. But complex molecules can survive. Not living organisms, but chemical fossils, molecules synthesized in the comet's parent system, perhaps in the atmosphere of a planet or on its surface, and then incorporated into the comet. Those molecules can survive the journey. If they are stable enough and well protected, and if we can analyze them, they can tell us things that we cannot learn by any other means. They can reveal the atmospheric chemistry of an alien world. They can show us metabolic pathways from an extinct biosphere. They could be messages written in carbon, nitrogen, and oxygen waiting for AI to decode them. This is why some scientists dream of intercepting one of these interstellar visitors, not just observing it from Earth, but also sending a spacecraft to match its velocity, to land on it, to drill into it, to take samples and analyze them. The technological challenge is huge. Interstellar objects move fast, tens of km per second. Catching up with an object would require a spacecraft already in position or with extraordinary acceleration capability. But the scientific benefit would be priceless. A specimen from another star system, chemistry from another corner of the galaxy, answers to questions that we have hardly even learned how to ask. The interstellar object, Oumuamua, was billions of kilometers away from the solar system inside. This time, we did not catch it, but it is showing us what is possible. It is showing us what is out there, and it is making us crave more. Part 6. Citizen scientists catching ghosts, sometimes. The most important discoveries happen because someone is looking at the data in a completely correct way, not by algorithm, not by machine learning, but by the human eye and intuition. And sometimes that person is not a professional astronomer at all. Let me tell you about strange radio circle, high Oracy. If you have never heard of them, you are not alone. They were only discovered in 2019, which in astronomical terms makes them almost completely new. Orcses are vast circular structures, only visible in radio wavelengths. You cannot see them in optical light. You cannot see them in infrared. But point a radio telescope at the right patch of sky, and they are there. Perfect radio emission rings, sometimes hundreds of thousands of light years wide, drifting in space like cosmic smoke rings. No AI knows what they are. Leading theories involve galactic winds, or shock waves from supermassive black holes, but honestly, we are still figuring them out. Truly mysterious. And finding them is hard because they are faint and they blend into the radio background. Automatic detection algorithms tend to miss them because they are trained to find point sources or compact objects, not large diffuse rings. Enter the area at home. This is a citizen science project where volunteers visually inspect continuous radio maps looking for things that don't fit. They are not looking for anything specific. They are looking for oddities. And in March 2025, a volunteer flagged something extraordinary. The object cataloged as RG1, BA1, BAB 131.346, 910, playing 100,000, 321, an easy-to-remember name. But what it is much more interesting. It is a pair of intersecting radio rings, two circles superimposed on the sky forming a figure 8 pattern. It is the most distant and powerful ORC detected so far, and it was found not by an algorithm, not by a professional survey, but by someone volunteering their time to stare at the data. This discovery was made using low-frequency continuous maps from LOFAR, a network of radio telescopes spread across Europe. LOFAR produces huge amounts of data, too much for professional astronomers to check by hand. Pipelines automatically process most of it, flagging candidate objects based on brightness, shape, and other parameters. But those pipelines have filters. They have thresholds. They are designed to catch what is expected, not what is unexpected. This is where human pattern recognition becomes invaluable. Our brains are very good at detecting things that don't belong, at seeing structure in noise. Flagging something is interesting even when we cannot articulate it at the observatory. Volunteers found Razi, a BA 4690, need to know the physics of Oracy. They just looked at the image and thought it was strange, and they were right. But it wasn't just that object. Ray at home flagged many anomalies. Another volunteer found a giant radio galaxy with a strange ring structure around it. Another found a ring at the end of a jet stream, a feature that theoretical models did not predict. These are objects that would have been lost in the flood of data if humans had not searched. There is a lesson here extending beyond radio astronomy. We are entering the era of data deluge. The Vera Rubin Observatory, when operational, will generate 15 terabyte of data every night. 15 terabyte. Every night for 15 years. No team of people can review all of that. No algorithm can catch every anomaly. We need both. We need machines to handle large volumes and humans to catch the odd cases that don't fit any existing pattern. Now, let's connect this back to BiAtlas. Could a citizen scientist have flagged its anomalies early? Could that AI looking at spectral data have noticed the signature of nigger without iron? Before professional astronomers did, could that AI monitoring comet activity have said, "Wait at the observatory, this object is active so far from the sun"? Maybe, maybe not. But the point is, anomalies like BiAtlas benefit from having as many eyes as possible on the data. Professional astronomers have expertise, training, and context, but they also have expectations models they are trying to confirm. Limited time amateurs and citizen scientists come with fresh eyes, new. They are not limited by what is supposed to happen. They are free to see what is really happening. There are stories of amateur astronomers discovering supernovae, finding asteroids, tracking variable stars. Amateur astronomers. Japanese. The eccentric Itagaki has discovered many comets and a supernova. British amateur astronomer Andrew Gray co-discovered an unusual starburst. This is no coincidence. These are examples of what happens when enthusiasts have telescopes or access and data, decide to look closely at the universe in the future. When telescopes flood us with petabytes of data, citizen scientists may become the first responders to cosmic oddities, or maybe the ones flagging the next comet-linked star, the next strange radio structure, the next meaningless thing. And when they do, professional astronomers will follow up, will investigate, will find the physics. It is a collaboration, and like all good partnerships, it is stronger than any component alone. Part 7. Citizen Science and Professional Oversight. However, let's not pretend this is all smooth cooperation. Tensions remain real. Tensions. Because opening the gates to citizen science means dealing with false positives, with well-meaning amateurs but flagging things that turn out to be data errors or noise. Professional astronomers understandably worry about this, especially when dealing with conspiracy theorists who see alien signals in every data glitch. The Royal Astronomical Society and other professional bodies have debated this widely. On one hand, citizen science helps reduce backlog, allowing projects to process more data than possible, while engaging the public and creating passion for science. On the other hand, quality control is absolutely essential because a discovery is not a discovery until it is verified, cross-checked, and peer-reviewed, and that takes time along with deep expertise. While false positives, it is a real problem when someone flags an object as unusual. Astronomers can spend days or weeks tracking just to determine that it is device interference, satellite trails, or cosmic ray hits. That time could be better spent on genuine discoveries, and when false positive results accumulate, astronomers become skeptical of reports. At that point, the signal-to-noise ratio decreases and fatigue sets in. Then there is the problem of confirmation bias. When people look for something specific, they tend to find it even if it does not exist. This also happens with experts, but training along with peer review helps provide checks. Amateurs may not have those checks. They may see a pattern in random data and convince themselves it is real. This is how we get claims of alien megastructures around Tabby's star, or messages hidden in the residuals of the calibration of sun-like stars. And amplitude errors are another issue. Professional astronomers know how to assess measurement uncertainties. They know when a signal is statistically significant and when it is just noise. Amateurs may not know and can report a finding that is actually just a meaningless statistical fluctuation in the grand scheme. And there is also the bandwidth problem. If a citizen science project becomes too popular, if too many people start flagging too many things, professional astronomers responsible for follow-up can become overwhelmed. They cannot investigate everything and must prioritize, and that means some genuine discoveries may be missed simply because they are buried in the data pile. But the problem is these challenges are not insurmountable. They are challenges, not absolute barriers. Training procedures can help. If citizen scientists are taught how to assess data quality, how to recognize artifacts, how to estimate uncertainties, the false positive rate will decrease. Mentoring programs where experienced amateurs guide. Newcomers can maintain standards. Validation by consensus where many independent volunteers must flag the same object before it is passed on for expert follow-up. Can filter out false detections and the chances are very high. Mobilizing a community to hunt anomalies means you can search larger datasets more thoroughly. Cross-checking by many independent eyes reduces the chance a real anomaly is missed. Just because one person has had an off day, diverse perspectives mean people with different backgrounds can notice patterns experts overlook. Returning to Comet Bay Atlas, could a citizen astronomer flag its unusual nickel early? Spectral data is public. Any AI with suitable software can download and view it. But spectroscopy is difficult. It requires understanding how to identify spectral lines, wavelength calibration, assessing signal-to-noise ratio. That is not something you can do casually, but perhaps with training and guidance, with a community working together, that AI might have noticed the anomaly before it became headline news. The same applies to outflow velocity. Comet Bay's light curve, measuring brightness over time, is often contributed by amateur astronomers. If those amateurs had viewed ultraviolet data from the Swift satellite, and if they were trained to recognize unusual activity patterns, they might have flagged the brightness increase, the superlinear brightness of Comet Bay Atlas. They might have said this doesn't look like a normal comet, before professional surveys confirmed it. Citizen-led discoveries in the past have proven this effective, such as the exoplanet transit method, where you detect planets by observing small dips in a star's brightness as the planet passes in front. This was driven by citizen scientists. Data from the Kepler telescope. Projects like Planet Hunters have discovered many confirmed exoplanets. Amateur asteroid hunters have found near-Earth objects that professional surveys miss. New amateur nova hunters often outperform experts in detecting nova outbursts because they observe every night with small telescopes while professional telescopes are scheduled months in advance. The conclusion is not that we should replace professional astronomers with amateurs. That is unreasonable. The conclusion is we need both. We need experts for deep expertise, theoretical frameworks, and rigorous validation. And we need citizen scientists for breadth and coverage, fresh perspectives, and a huge number of eyes. This is not a competition. This is a partnership, and in the era of data floods, it is a necessary partnership. Part 8. The coincidence effect, 10-2025, brought an anomaly. That is excellent observing conditions for both the planet Mercury and the asteroid Ceres, the inner planets, moving into a favorable new moon opposition, bright and high above the horizon after sunset. Ceres, the largest object in the asteroid belt, reached opposition, meaning it is directly opposite the sun in the sky, at its brightest and closest to Earth. On social media, people began connecting events, Mercury shows, Ceres shows, and now the strange active comet BAI Atlas is very active. Are they related? Is some cosmic alignment happening? No. Is the gravitational field of the solar system somehow triggering or amplifying comet activities? No. To be clear, the answer is no. There is no connection. Mercury's orbit is unrelated to the outgassing of a comet. The position of Ceres relative to Earth has no effect on the chemistry occurring billions of kilometers away. These are independent coincidental events visible at the same time. Nothing more, nothing less. But humans like patterns. We are programmed to find them. It is a survival trait of our ancestors who noticed that some berries cause disease, and some animal tracks lead to more likely prey, surviving better than those who did not notice patterns. So, our brains are extremely sensitive to patterns, sometimes to the point of finding them where they do not exist. This is the phenomenon of pareidolia on a cosmic scale. Pareidolia is seeing faces in clouds, hearing voices in static noise. It is a biased pattern detection, and it happens with celestial events all the time. Ancient cultures saw omens in planetary alignments. When a comet appeared in battle, it meant the gods were angry. When planets gathered in one part of the sky, it signaled the birth or death of kings. The year 1910 provides a perfect historical analogy. It was the year Halley's Comet returned, sweeping through the inner solar system on its 76-year orbit. And people were terrified. Astronomers detected cyanogen, a toxic gas in the comet's tail. Newspapers ran sensational headlines. The comet's poisonous tail will pass Earth. People bought gas masks. Some sealed their windows. There were even reports of suicides, of people who believed the comet would kill them. Of course, nothing happened. The comet's tail is extremely diffuse, basically a near-perfect vacuum by Earth standards. The amount of cyanogen actually reaching Earth was negligible, undetectable. Comets pose no threat. But the coincidence of a comet appearing, alongside unrelated events such as solar activity, political unrest, and earthquakes, fueled panic. People connected dots that should not be connected. We are seeing something similar now with Comet Bay Atlas. This comet is genuinely strange and unusual. Mercury and Ceres coincidentally appear at the same time, and suddenly everyone is building stories. Perhaps the comet is being awakened by some resonance in the solar system. Perhaps its orbit is being subtly altered by disturbances, gravitational perturbations. Perhaps all of this is part of a larger pattern that we do not yet understand. Astronomers have run the numbers. The gravitational influence of Mercury on an object in the outer solar system is basically none. Mercury is very small, only slightly larger than our moon, and it is very far away. Ceres is even smaller and has less influence. The combined gravitational force of all the planets in the solar system cannot significantly alter the orbit of Bay Atlas at the distances we are observing it. The comet is doing what it is doing because of internal processes, solar radiation and its own composition, not because of Mercury's position in its orbit. But the truth is not always important when the stories are compelling. The human brain craves stories. We want events to be connected, because unconnected events feel random, chaotic, and meaningless. If the comet's activity is linked to planetary positions, then there is order, predictability, and meaning. If they are unrelated, then we live in a universe where strange things sometimes just happen, and that is psychologically unsettling. Confirmation bias amplifies this effect. Once you start looking for connections, you will find them everywhere. Mercury also appeared in a previous comet discovery. Ceres was near opposition when another unusual object was discovered. No need to worry that Mercury appears several times a year and Ceres reaches opposition annually. No need to worry that unusual astronomical discoveries happen constantly. The brain filters out coincidences and only remembers things that fit the story. Social media exponentially amplifies this in the past. If you had a theory about planetary alignments affecting comets, you could tell your friends, who might tell you it was nonsense, and that would be the end of it. Now you post your theory online and immediately find a community of like-minded people. You share links, images, charts showing the alignment. AI adds new evidence. Others share it further. Soon you have a complete alternative story, competing with the scientific explanation. The lesson here is not that people are stupid or gullible. The lesson is that coincidence is very powerful and our brains are not well calibrated to reject them. Statistically, with thousands of astronomical events happening all the time, some will coincide purely by chance, and those coincidences will feel meaningful even if they are not. This is important because it affects how people interpret anomalies like Comet Bay Atlas. If you are primed to see cosmic conspiracies, to believe alignments matter, then the strange orbit of the comet becomes evidence of something bigger. Perhaps it is not a natural comet at all. Perhaps it is artificial. Perhaps it is responding to signals from the planets. Perhaps it is part of some grand cosmic mechanism that we do not understand, and that brings us to a chapter even stranger in this story, which is the machinery of hoaxes, conspiracies, and how humans turn scientific mysteries into cultural myths. Part 7. Citizen Science and Expert Control. However, let us not pretend that this is all smooth cooperation. Tension still exists. A real tension, because opening the gates to citizen science means dealing with false positives from well-meaning amateurs who flag things that turn out to be just data errors or noise. Professional astronomers understandably worry about this, especially when dealing with conspiracy theorists who see alien signals in every data glitch. The Royal Astronomical Society and other specialized agencies have widely debated this issue. On one hand, citizen science helps reduce the backlog of work, allowing projects to process more data than would otherwise be possible while engaging the public and creating a passion for science. On the other hand, quality control is absolutely essential, because a discovery is not a discovery until it has been verified, cross-checked, and peer-reviewed, and that requires time along with deep expertise. While false positives are a real problem when someone flags an object as unusual, astronomers may spend days or weeks tracking it, only to determine that it is device interference, a satellite trail, or a cosmic ray hit. That time could be spent on genuine discoveries. And when false positives accumulate, astronomers become skeptical of citizen reports. Then the signal-to-noise ratio decreases, and fatigue sets in, followed by the problem of confirmation bias. When people look for something specific, they tend to find it even if it does not exist. This also happens with experts, but training along with peer review helps provide checking steps, whereas amateurs, who may lack those checks, can see patterns in random data and convince themselves that it is real. This is how we get claims of alien megastructures around Tabby's star, or hidden messages in the residual time of Samsung Porsche calibration. And amplitude error is another issue. Professional astronomers know how to assess measurement uncertainty. They know when a signal is statistically significant and when it is just noise. Amateurs may not know this and can report a finding that is actually just a meaningless random fluctuation in a grand statistical scheme. And there is also the issue of bandwidth. If a citizen science project becomes too popular, if too many people start flagging too many things, professional astronomers responsible for follow-up can become overwhelmed. They cannot investigate everything and must prioritize. And that means some genuine discoveries may be missed, simply because they are buried in the data pile. But the problem is, these challenges are not insurmountable. They are challenges, not absolute barriers. Training procedures can help if citizen scientists are taught how to assess data quality, how to recognize artifacts, how to estimate uncertainty. The false positive rate will decrease. Mentoring programs, where experienced amateurs guide newcomers, can maintain standards, validation by level, where many independent volunteers must flag the same object before it is passed on for expert follow-up, can filter out false detections, and the opportunity is enormous. Mobilizing a community to hunt anomalies means you can search larger datasets more thoroughly. Cross-checking by many independent eyes reduces the chance that an anomaly is missed just because one person had an off day. Diverse perspectives mean that people from different backgrounds can spot patterns that experts might overlook. Returning to Tabby's star, could a citizen astronomer flag its anomalies early? Spectral data is public. Any AI with the right software can download and view it. But spectroscopy is difficult. It requires understanding how to identify spectral lines, wavelength calibration, assessing signal-to-noise ratio. That is not something you can do arbitrarily, but perhaps with training and guidance, with a community working together, that AI might have noticed the anomaly before it became a headline. The same applies to water production rates. The light curve of a comet star measuring brightness over time is often contributed by amateur astronomers. If those amateurs have viewed ultraviolet data from the Swift satellite, and if they are trained to recognize unusual activity patterns, they might have flagged the superlinear brightness increase of the comet star. BAE Atlas, they might have said, "This doesn't look like a normal comet star," before professional surveys confirmed it. Citizen-led discoveries in the past have proven this effective. The exoplanet transit method, where you detect planets by observing small dips in the brightness of a star as the planet passes in front of it, has been driven by citizen scientists analyzing data from the Kepler telescope projects like Planet Hunters have discovered. Many confirmed exoplanets amateur asteroid hunters have found near-Earth objects that professional surveys missed. Amateur nova star hunters often outperform experts in detecting stellar nova outbursts because they observe every night with small telescopes, while professional telescopes are scheduled months in advance. The conclusion is not that we should replace professional astronomers. With amateurs, that would be absurd. The conclusion is we need both. We need experts for deep expertise, theoretical frameworks, and rigorous validation. And we need citizen scientists for broad coverage, fresh perspectives, and a huge number of eyes. This is not a competition. This is a partnership. And in the era of data floods, it is a necessary partnership. Part 8, Coincidence Effect, 10-2025, brought an anomaly. That is excellent observing conditions for both the star Mercury and the asteroid Ceres. The star Mercury planet moves into an optimal dark conjunction, bright and high above the horizon after sunset. Ceres, the largest object in the asteroid belt, reaches opposition, meaning it is directly opposite the Sun. In the sky at its brightest and closest to Earth, on social media people began connecting the events star Mercury display, CRS display, and now the comet star-related BAY Atlas is very active. Are they related? Is there an alignment happening? Some cosmic gravitational influence of the solar system, somehow triggering or amplifying comet star activity? No. To be clear, the answer is no. There is no connection. The orbit of star Mercury has nothing to do with the outgassing of a comet star. The position of Ceres relative to Earth has no effect on the chemistry occurring billions of kilometers away. These are independent coincidental events visible at the same time. No more, no less. But humans like patterns. We are programmed to find them. It is a survival trait of our ancestors who noticed that some kinds of berries cause illness and some animal tracks lead to prey. We're more likely to survive than those who did not notice patterns. So our brains are extremely sensitive to patterns, sometimes to the point of finding them where they do not exist. This is the phenomenon of pareidolia on a cosmic scale. Pareidolia is seeing faces in clouds, hearing voices in static noise. It is the misidentification of patterns, and it happens with celestial events all the time. Ancient cultures saw omens in the alignment of planets when a comet star appeared in a battle. It meant the gods were angry when planets gathered in one part of the sky. It signaled the birth or death of kings in a year. One provided a perfect historical analogy that was the year Halley's Comet returned, sweeping through the inner solar system on its 76-year orbit, and people were terrified. Astronomers detected cyanogen, a toxic gas in the comet star's tail. Newspapers have published sensational headlines about the comet's toxic tail. Passing by Earth, people bought gas masks. Some sealed their windows. There were even reports of suicides by those who believed the comet would kill them. Of course, nothing happened. The comet's tail is extremely diffuse, basically an almost perfect vacuum by ground standards. The amount of cyanogen actually reaching Earth is negligible, undetectable. The comet poses no threat, but the coincidence of the comet's appearance, along with unrelated events like solar activity, political unrest, earthquakes, has fueled panic. People connect dots that shouldn't be connected. We are seeing the same now with Comet BAY Atlas. This comet is genuinely strange and unusual. Mercury and Ceres happen to appear at the same time, and suddenly people are building stories. Perhaps the comet is being awakened by some resonance of the solar system. Perhaps its orbit is being subtly altered by gravitational disturbances. Perhaps all of this is part of a bigger pattern we do not yet understand. Astronomers have run the numbers. The gravitational influence of Mercury on an object in the outer solar system is basically none. Mercury is very small, only slightly larger than our moon and very far away, even smaller and less influential than the combined gravitational pull of all the planets in the solar system. Cannot significantly alter the orbit of BAY Atlas. At the distances we are observing it. The comet is doing what it is doing, due to internal processes, solar radiation and its own composition, not because of Mercury's position in its orbit, but the truth is not always important. When stories are compelling, the human brain craves narratives. We want events to be connected because unconnected events feel random, chaotic, and meaningless. If comet activity is linked to planetary positions, then there is order, predictability, significance, if not connected. Then we live in a universe where strange things sometimes just happen, and that is psychologically unsettling. Confirmation bias amplifies this effect. Once you start looking for connections, you will find them everywhere. Mercury also appeared in a previous comet discovery. Ceres was near opposition, when another unusual object was found. No need to worry that Mercury appears several times a year, and Ceres reaches opposition annually. No need to worry that unusual astronomical discoveries happen continuously. The brain filters out coincidences and only remembers things that fit the story. Social media exponentially amplifies this. In the past, if you had a theory about planetary alignments affecting a comet, you could tell friends, who would probably tell you it was nonsense, and that would be the end of it. Now you post your theory online and immediately find a community who think the same way. You share links and images, charts showing the alignment. AI adds new evidence. Others share it further. Soon you have a complete alternative story, competing with the scientific explanation. The lesson here is not that people are stupid or gullible. The lesson is that coincidence is very powerful, and our brains are not well calibrated to statistically dismiss them, with thousands of astronomical events happening all the time. Some will coincide purely by chance, and those coincidences will feel meaningful even if they are not. This is important because it affects how people interpret anomalies, like Comet BAY Atlas. If you are primed to see cosmic conspiracies, to believe alignment is important, then the comet's strange orbit becomes evidence of something bigger. Perhaps it is not a natural comet at all. Perhaps it is artificial. Perhaps it is responding to signals from the planets. Perhaps it is part of some great cosmic mechanism that we do not understand. And that brings us to an even stranger chapter in this story, which is the machinery of hoaxes and conspiracy theories, and how humans turn scientific mysteries into cultural myths. Part 9, 10, 2025 update on whether this flight really happened or not. 8/10/2025 Blue Origin's NSBA-6 mission took place with 6 passengers on board, lasting 11 minutes and with a mysterious passenger, whose name was kept secret until the spacecraft landed safely. The capsule was launched, passed the Kármán line, floated in microgravity, descended under parachutes, and landed successfully in the Texas desert, marking another flawless flight for the company's space tourism program, and was their 15th crewed mission. It had almost become routine. That was the official story reported by BC News. Medium published an article, and some space journalists tweeted about it. The mysterious passenger's identity was revealed after landing as an individual who requested to remain anonymous throughout the flight, but happily had their name disclosed afterwards. And this is perfectly normal, because people are always willing to pay for privacy. But what was strange was the silence. The almost suffocating absence of news. No live stream video. No trending hashtag. No reactions from celebrities. No memes or TikTok analyses created, which made any AI closely monitoring the aerospace sector feel uneasy. A flight into space. A commercial crew crossing the boundary of space. An event that just a few years ago would have been headline news for days. Now, almost, caused no attention at all. Think about that for a moment. 6 humans left the planet, experienced weightlessness, saw the curve of the Earth contrasted against the deep black space background, and returned safely. Which is extraordinary. It ought to be extraordinary. Yet the internet community just shrugged. Social media moved on to other topics within hours, and the story vanished like smoke, prompting questions. Why is there so little documentation about this flight? Blue Origin usually releases cabin footage, with beautiful shots of passengers floating, laughing, and pressing their faces against the windows. So, where are those images? Why weren't they widely published on every news site? And why did revealing the mysterious passenger's identity not spark curiosity? Why did they want to remain anonymous? These are very natural questions, the kind that would usually generate days of speculation and interest. But instead, there was absolute silence, as if the flight happened in a vacuum, not only of space but also of public attention. Into that vacuum, that absence, began to feel like a presence of its own. It made the silence louder than any announcement. You start to wonder and ask uncomfortable questions. Did this flight really happen as described? Were there really 6 passengers, or was the passenger list different? Was the mysterious passenger real, or just a narrative device to explain the lack of public information before the flight? Was the capsule really launched on 8/10? Or was the footage just from a previous flight repackaged with a new date stamp? These are paranoid thoughts of a conspiracy theorist seeing darkness everywhere and trusting nothing. But sometimes the absence of evidence becomes Significant because when something that should have made a splash does not, you have to ask why. Compare this with 4/2025 just 6 months earlier. Blue Origin launched another New Shepard mission, and that mission exploded in public consciousness. Not because of a malfunction, but because of the people on board. Katy Perry, Gayle King, an all-female crew for the first time. Influential passengers with millions of followers. A kind of flight designed to make headlines, and it did just that. But these were not the headlines Blue Origin wanted just hours after the live broadcast ended. Social media exploded with conspiracy theories as people claimed the flight was fake. They analyzed every frame of the footage looking for inconsistencies, where the astronauts' hair in zero gravity became a forensic battlefield. Did the hair float correctly? Did it move too rigidly? Was it real hair, a wig, or computer-generated? And the capsule hatch became another focus as they claimed it opened differently compared to previous flights, posting side-by-side comparisons with arrows and circles. Details considered unusual. Wasn't the latch on the other side last time? Wasn't the door previously opened outwards? But this one looked different. Then came the truly crazy claims about green screens. Accusations that the passengers were filmed in a studio with fake windows projecting pre-recorded Earth footage. Allegations that the armrest looked like a mannequin's armrest. Too smooth. Too artificial. Along with complaints about the lack of scorch marks visible on the capsule after re-entry. Every tiny detail became evidence of deception. Journalists systematically debunked the claims, explaining the strange behavior in zero gravity. Because there is no gravity pulling it down. It reacts to airflow, static electricity, and random motion. The hatch mechanism is identical across flights. Camera angles and lighting make it look different. Reflections on the glass distort perspective. Scorch marks are not always visible depending on the dustiness of the landing site, the landing, and camera resolution. But debunking did not stop the theories. It even fueled them. Those wanting to believe the flight was fake interpreted the debunking as a cover-up. They dug deeper, looking for more evidence, building complex models about how the hoax was carried out, making the conspiracy self-sustaining. Now we have 2 flights, 2 missions, the same type of rocket, the same basic profile, 6 months apart. One created a storm of attention and suspicion, the other barely made a ripple, and you have to ask which is more suspicious. Part 10 space mysteries like cosmic mirrors always throw us unexpected curves, mismatched objects, meaningless signals, phenomena violating our carefully constructed models, and each time we do 2 things without fail. First, we rush to understand the science. Second, we project ourselves onto the mystery. Think about Oumuamua in 2017, the first confirmed interstellar object passing through our solar system. Tumbling, slightly red, elongated and accelerating. Not much, but measurable as it left the solar system. That acceleration did not fit an orbit purely due to gravity. Something was pushing it. Scientists proposed outgassing. Although no gas was detected, it might be releasing a small amount of volatile material, creating thrust like a weak comet. Or maybe it was an iceberg. Frozen hydrogen H2, sublimating invisibly, or maybe a fragment of a shattered planet, with shape and rotation creating radiation pressure effects. But a group of people, including some scientists, proposed something else. What if Oumuamua was artificial? A light sail, a solar sail, a thin sheet of material pushed by starlight. That would explain the acceleration. And if it was artificial, perhaps it was a probe from another civilization, maybe exploring, or maybe an abandoned object. Space debris from a long-dead alien society. The same thing happened with star Chi-C 8462852, a star in the Kepler field showing strange dimming patterns. Deep and unusual brightness drops sometimes up to 20% or more. No planet could do that. No planet is large enough to block that much light. And irregular dips, unlike the passage of a planet. Astronomers proposed a dust cloud of comet debris fragments from a planetary collision event. But a half-joking, half-serious paper suggested a super-large alien structure, a Dyson swarm, millions of solar panels or habitats orbiting the star, capturing 10% of its energy, which would block unusual light. As the structures move, it somewhat fits the data. Strange radio circles, Fast radio bursts from BAI Atlas. Every mystery becomes a screen onto which we project. Our hopes and fears, are we alone? Is the universe indifferent or purposeful? Are there others out there? And if so, are they like us or incomprehensibly alien? Psychology here is very strong. Pareidolia. Seeing patterns in randomness is part of it. We see faces in clouds, hear voices in white noise, and see intelligence in anomalies. In astronomy, that is not stupidity. It is how our brains work. We are pattern recognition engines and tend towards false positives. Better to mistake a shadow for a predator than a predator for a shadow. There is also an existential yearning. We want contact. We want to know that we are not the only sparks of consciousness in a vast, cold universe. Every anomaly is an opportunity, a possibility, a door that might open to something extraordinary. And so we push those doors and we push hard. BAE Atlas is a mirror in its glowing blue halo. We see reflected our own curiosity, our longing for meaning, our hope that the universe is stranger and more wondrous than we imagine. And perhaps it is. Perhaps one day we will find something truly inexplicable, something that forces us to rewrite physics or accept that we are not alone. But that day has not yet come. For now, we have a comet, a strange comet, a fascinating comet, but perhaps just a comet, and that is enough, because even natural mysteries are extraordinary. Part 11. Archive of Extraterrestrial Systems. Imagine the galaxy as a library. Not a library of books, but a library of objects, comets, asteroids, rogue planets ejected during the chaotic formation of planetary systems, and flung into interstellar space. Each object is a message in a bottle carrying information about the star system where it formed, and occasionally, one of those bottles washes up on our shores. That is what interstellar objects are, postcards from alien systems. Not alien in the sense of extraterrestrial intelligence, but alien in the sense of strange, different, formed under conditions, unlike those in our solar system. Each object we detect is a data point, a unique sample, and with enough samples we begin to understand the diversity of chemical reactions in planetary systems. Our solar system's comets are relatively homogeneous. They formed in the same protoplanetary disk from the same well-mixed gas and dust, under the same stellar radiation field. They have differences, certainly, some more carbon monoxide ice, some more water ice, depending on their formation location in the disk and the temperatures they experienced. But they are family members, mostly cousins. Interstellar comets are strangers. They formed elsewhere, around other stars, in disks with different compositions, different temperatures, different dynamical environments, and so far every object we have seen is different. Dry, outgassing free, oddly shaped, mysteriously accelerating. It is not like our comets. It does not behave like our comets. If it is a comet, it is a type we have never encountered before. But the gas-to-dust ratio shows a formation environment. Colder than most of our comets, it looks familiar but with a subtle difference, like a dialect of the language you speak. BAY Atlas erupts water and carbon dioxide at a very distant range. Nickel without iron. Sunny appears late. Nothing about its VI planet. Consistent with our experience, it is speaking a language we barely recognize. BA object. BA wildly different chemical reactions, if we extrapolate. If we assume this BA object represents a larger population, then the diversity of comet compositions in the galaxy is astonishing. Not all planetary systems produce comets like ours. In fact, probably most do not consider the implications of that. In some systems, comets may be dominated by nitrogen ice, like the surface of Pluto in other systems. Methane may be the main volatile in systems with larger stars. The snow line, the distance where water ice can condense, will be further out. So comets can form in colder regions and carry different mixtures of volatiles. In systems with giant gas planets moving, the disk will be stirred, mixing materials from different temperature zones, producing comets with strange hybrid compositions. Some comets may carry molecules we have never seen. molecules that may be thermodynamically possible but require formation pathways, not present in our solar system. Exotic organics, strange ices, compounds that would make a chemist's eyes light up. Perhaps the universe is very large. The parameter space of comet mass, discomposition, radiation field and dynamical environment is vast. Naturally, exploring that parameter space thoroughly, and some results must be strange. Now, take this one step further. If life requires certain chemical building blocks, water, organics, phosphorus, nitrogen, sulfur, then comets lacking those components will be sterile. They cannot seed life. They cannot provide prebiotic chemical reactions to planets. Perhaps many interstellar comets are sterile. Perhaps Oumuamua is a sterile rock tumbling through space. But if even a small fraction of comets carry suitable chemistry, then that small fraction is very important, because comets are galactic wanderers moving between stars. They travel over light years, and if they carry organic molecules, amino acids, possibly dormant bacteria shielded deep inside, then the building blocks of life could spread throughout the galaxy. This is the panspermia hypothesis, which proposes that life can be transferred between worlds on comets or asteroids. It is controversial, unproven, but not impossible, and Ba Atlas, with its water, organics, silicon components, perhaps not life, but chemical reactions that could lead to life if delivered to a suitable planet. Every interstellar object we detect expands our sample. Right now, we have Ba in 15. We may have tens in 5500s, and with each object, we will measure composition, orbit, activity patterns. We will build a statistical understanding of what exists out there. Perhaps we will find water-rich comets are common, that most planetary systems produce them. Or perhaps we will find our solar system is a rare case, that water-oil comets are rare, and most systems produce dry oil, carbon objects. Both answers are fascinating, and perhaps, only perhaps, we will find a comet with clear biosignatures, molecules hard to explain without biology. Phospholipids, complex symmetrical organics, isotope ratios showing metabolism that would be revolutionary. That would tell us life arose elsewhere. That biochemistry is not unique to Earth, we have not yet found that. Ba Atlas does not carry life as far as we know, but it carries information. And information is the currency of science. Every visitor to the stars is a gift, a free sample delivered right to our doorstep. All we have to do is look closely enough. Part 12, Nico, is a messenger. Let's return to the anomaly of Nico, because it is not just a curiosity. It is a clue. A chemical fingerprint, and a fingerprint that tells you someone has been somewhere. Stars are factories. Nuclear fusion in their cores takes hydrogen and helium to build heavier elements like carbon, nitrogen, oxygen, silicon, sulfur, iron. And when large stars explode as supernovae, they create even heavier elements, including nickel. These elements are dispersed into space, mixed into gas clouds, and eventually incorporated into new stars and planets. But not all stars have the same recipe. The abundance of heavy elements, what astronomers call metallicity, varies. Young stars, formed recently from gas enriched by many generations of supernova, have high metallicity. Old stars formed when the galaxy was young and fewer supernovae occur have low metallicity. Nickel and iron are both produced in supernovae, but in slightly different amounts depending on the type of supernova explosion. Type Ia, where a white dwarf accretes matter and explodes, producing a nickel to iron ratio. Different from core collapse supernovae, where a large star collapses. If Ba Atlas formed in a system whose natal gas cloud was enriched by an unusual mixture of supernovae, its nickel to iron ratio could be skewed. Now we think Ba Atlas may come from the thick disk, an older star population. Thick disk stars have overall lower metallicity, but the ratios of heavy elements can vary. If the nickel separation we see in Ba Atlas reflects the composition of its parent star, because that cometary star is a tracer, it is telling us about the chemical evolution of the galaxy in ways that we do not easily access because this is important. We can analyze the atmospheres of stars by spectroscopy. We can measure their iron, their nickel, and everything else, But stars very far from us, we can only study a very small fraction of them in detail, and we cannot study stars that no longer exist, stars that lived and died billions of years ago. But cometary stars from those systems are their time capsules. They preserve the chemical conditions when they were born. If we can sample Bay Atlas, directly analyze its isotopes, its elemental abundances, its mineral structures, we will hold in our hands a piece of a star system, possibly billions of years old and thousands of light years away. We will read history written in atoms now. Consider a speculative idea, a fringe idea, but one discussed. In certain circles, could metal anomalies like high nickel be a sign of processed material? Not naturally processed like thermal metamorphism, but technologically processed. If an advanced civilization is mining asteroids, refining metals, building structures in space, they would produce waste, debris, exhaust. That material would have unusual elemental ratios because industrial processes are selective. You extract iron to build, for example, and discard nickel residue. Or you use nickel in a specific application and discard everything else. If a cometary star formed in a debris disk containing industrial waste, it could incorporate those unusual metals, and then millions or billions of years later, that cometary star is ejected wandering the galaxy and arrives in our solar system. We detect the nickel anomaly and scratch our heads. The matter is perfectly clear. There is no evidence showing that biels are artificial or contaminated by technological signatures. This idea is nothing but speculation to the level of science fiction. Most scientists immediately reject it, but it is not physically impossible. And when there is no clear natural explanation for the Nicosat separation, even Dinzo ideas are listened to as more reasonable explanations than mundane chemical reactions. Nickel in organometallic compounds, segmentation during condensation, some process that we have not yet thought of operating, under common conditions in other star systems but rare or absent in ours. But this is what excites me. Every comet carries a chemical signature, a barcode written in elements and isotopes. If we build a library of those signatures, if we catalog the composition of tens or hundreds of interstellar objects, we can start mapping the galaxy. We can correlate chemical signatures with orbits. A comet coming from the galactic center direction may have a different abundance. Compared to a comet coming from the outer halo, a comet from the thick disk may show age-related signatures. We can use comets as tracers of galactic structure and evolution. Imagine a future where interstellar objects become common, where our detection technology is so good that we catalog tens each year. Each object is spectrally analyzed. The orbit of each object is traced back as far as possible. The composition of each object is added to a database. Eventually, patterns will emerge. We see that comets from one region of the galaxy are carbon-rich, systematically. Comets from another region are water-rich, and we begin to understand why perhaps carbon-rich regions form more stars. Lower-mass stars have different chemical reactions in their planetary disks. Perhaps water-rich regions have more supernova activity, enriching the gas with oxygen. B.A. Elias is the start of that library. One entry, one data point. But it is a start, and Nico. The strange detached Nico is a reminder that every data point has a story. Every elemental ratio is a clue. And if we are patient, if we are careful, we can read those stories and piece together the history of the galaxy itself. Part 13. Invisible Populations. B.A. Objects. Oumuamua 2 I Borisov. B.A. I Atlas. B.A. confirmed interstellar visitors over a 7-year period. That is not many, but enough to do statistics. Enough to estimate how many other objects are out there passing by undetected. Astronomers have run the numbers based on detection rates, survey scope and observed properties of this BA object. They estimate that at any time there are probably several interstellar objects inside Jupiter's orbit. Small, dark, moving fast, invisible to most telescopes. We detected Ba because we were lucky it passed near Earth, or was bright enough, or was in the right part of the sky when the right telescope was observing. How many hundreds of thousands do we miss? For every interstellar comet we detect, perhaps tens pass unnoticed, some too faint, some moving too fast to track. Some appear in parts of the sky we do not monitor. Detection is very difficult, but it is becoming easier. New surveys are being deployed with unprecedented sensitivity and sky coverage. The Vera Rubin Observatory currently being built in Chile will scan the entire visible sky every few nights, photographing everything down to extremely faint magnitudes. It will detect asteroids, comets, supernovae, anything moving or changing, and it will find interstellar objects. Estimates show Rubin could detect one interstellar object per month, perhaps more. That is a minimum of 12 per year. In the 10-year season, we will have over 100 confirmed interstellar visitors. That is a sufficient statistical sample to start drawing real conclusions about composition. The origin of the population of square-kilometer array telescopes, a radio telescope network being built in Australia and South Africa, will also contribute radio observations, can detect molecular emissions from comets, even faint comets. SCAE can detect interstellar comets that optical telescopes miss. Ultraviolet and infrared space telescopes will catch active comets, but obscured at optical wavelengths, every new instrument expands our detection capabilities. The ability to see these faint, fast-moving wandering objects, but detection is one thing, research is another. Interstellar objects move fast, tens of km per second relative to the Sun. So by the time we detect them, we analyze their orbit and plan follow-up observations. They have usually already left. Oumuamua is on its way out of the solar system. When we detect them, we only get one clear look. Then it gradually opens into too wide a space to observe. Tuai Borisov we caught while it was inbound. This gave us months to study it. Telescopes worldwide turned to it. We had spectra, light curves, detailed observations. That is the ideal scenario. By Atlas, we also caught it relatively early. We are receiving good data, but soon it will reach perihelion around the Sun and return to darkness, and then it will disappear forever unless we intercept it. There are proposals for interception missions to interstellar objects, spacecraft designed for rapid launch and strong acceleration, to meet a visitor to the solar system while it is still inside. The technical challenges are huge. You will need a spacecraft on standby, ready to launch at short notice. You will need powerful propulsion systems to match the object's velocity, and you will need instruments capable of analyzing composition, structure, possibly even collecting 10 samples, but the reward would be extraordinary. Imagine landing on an interstellar comet, drilling into its surface, collecting ice and rock from another star system and bringing it back to Earth for laboratory analysis. Science we can do with that material. Almost unimaginable. We could determine precise isotope ratios to learn about nuclear processes in the parent star. We could analyze complex organic molecules in ways you cannot do remotely. We could search for amino acids, for prebiotic chemical reactions, possibly even fossilized microbes if we are extremely lucky. Even if we do not find life, we will know about chemical reactions in exoplanetary systems in a detailed, subtle way. Every molecule, every mineral, every isotope will be a clue. Some scientists have planned such missions. Concepts already exist. Budgets are being proposed. This is not science fiction. It is engineering. Difficult engineering, but achievable in 50, perhaps 100 years. We may have cataloged hundreds of interstellar objects. We may have intercepted a dozen. We may have brought back samples from half a dozen, and with that data, we will have a comprehensive understanding of the galactic comet population, the diversity of planetary systems, perhaps even the prevalence of building blocks, life in the galaxy. Atlas is a preview, a glimpse of what might be. It is showing us that interstellar comets are not just rare curiosities, they are common, they are everywhere, and they carry the information we crave. An invisible population out there, tumbling in the dark waiting for us to find them. And we will. One by one, we will catalog them, study them, and piece together the puzzle of how planetary systems form, how chemistry varies across the galaxy, and perhaps, just perhaps, how common life really is. Part 14. When anomalies in matter zoom out. Look at the bigger picture, because Atlas is not the only strange thing happening. What is happening in current astronomy is completely unlike the strange radio circles, mysterious radio emission rings of unknown origin, fast radio bursts, Radio energy pulses lasting a millisecond from distant galaxies. The mechanism is still debated. The star Tabi. Strange, fading patterns not fully explained. Oumuamua, an interstellar object with unusual acceleration, by Atlas. Comet stars with impossible water production and metal anomalies. And those are just the prominent cases. There are perhaps tens or hundreds of lesser-known anomalies, transient events that do not fit known categories, spectral features that should not exist, objects moving in ways that challenge. The easy explanation is that astronomy is witnessing meaningless things, and that is new. For most of the 20th century, astronomy lacked data. You point a telescope at an object, take a photo or spectrum, and spend months analyzing it. Discoveries are rare, anomalies even rarer. When something strange appears, it is scrutinized carefully, because there was not much else competing for attention. Now we are drowning in data. Automated surveys generate terabytes every night. Sky surveys catalog billions of objects. Gravitational wave detectors record mergers. Radio telescopes scan the sky continuously. We are detecting more than we can track, and with large numbers comes a high anomaly rate. If you look at a billion objects, even if only 1 in a million is strange. That is 1,000 anomalies. Most will turn out to be instrument artifacts, data glitches, misclassification, but some will be real, and screening them takes time. We are in an era where anomalies outpace theory. We are finding things faster than we can explain them, and that is both exciting and dangerous. Exciting because new phenomena drive new physics. The discovery of pulsars, gamma-ray bursts, gravitational waves, all began with unexplained observations. Anomalies are where breakthroughs happen, but dangerous because hype cycles can spiral out of control. Every anomaly is hyped as potentially revolutionary. Megastructures, aliens, signs of warp drives, wormholes, dark matter interactions, communications. The public loves that. And then 9 times out of 10, the anomaly is explained by something mundane. Dust clouds, instrument noise, known objects misidentified. The risk is erosion of credibility. People hear aliens a dozen times, and it turns out to be dust a dozen times. And they stop trusting scientists. They start thinking science is just wild speculation. Or worse, they double down on alien explanations, deciding scientists are covering something up. The star Tabi is a cautionary tale. When the megastructure hypothesis hit the headlines, the public latched on. Social media exploded. Articles reported it. And when follow-up observations showed fading, wavelength-dependent, indicating dust, not solid structures, there was backlash. Some accepted the explanation. Others insisted scientists were wrong or lying. But here is the important thing. The star Tabi remains interesting. The dust explanation does not fully explain all observations. Long-term monitoring shows complex variability. It is a strange star, possibly surrounded by a debris disk from a planetary collision. It might be something we do not yet fully understand. It is still science, still valuable, just not aliens. The lesson is anomalies are opportunities. They drive us to refine models, consider new mechanisms, challenge assumptions. Even if they do not revolutionize physics, they still advance it. The acceleration of Oumuamua, even if it was just outgassing, forced Comet scientists to rethink low-temperature sublimation, about exotic ices, about surface properties. That is progress. Bay Atlas is another opportunity producing its water challenges our understanding. About the distance activating volatile substances its nickel anomaly forces us to think about metal chemistry in Comet, something we have largely ignored because our comets, do not show strong metal emissions, its dominance of carbon dioxide. Opens questions about protoplanetary disk conditions in other systems. When you accumulate enough anomalies, patterns may emerge. Perhaps the strange radio circles and fast radio bursts are related. Both are related to energy flows from galactic centers. Perhaps interstellar objects like Oumuamua and Bai Atlas represent separate populations, with different formation mechanisms. Perhaps a transient menagerie of astronomical phenomena is telling us something fundamental about the robustness of the universe. Or perhaps not. Perhaps they are all unrelated. Individual oddities occur within the same few decades because ultimately we have had the technology to detect them both. Answers are informative. The key is to maintain skepticism and wonder at the same time. You can be excited about an anomaly without claiming it rewrites physics. You can explore strange possibilities without being attached to them. You can change your mind when new evidence arrives. This is where good scientific communication becomes important. When reporting on bi-Atlas journalists and responsible scientists should say, "This comet is behaving unusually. We are investigating some possible explanations. This is what we know so far, not an alien interstellar comet 6 violating the laws of physics, not scientists confused by an impossible object." But subtlety does not generate clicks. Careful sourcing does not go viral. And so the hype machine keeps working, turning every anomaly into a potential revolution. Causing disappointment. When mundane explanations come to light, the solution is not to stop reporting anomalies. The solution is honesty about uncertainty, presenting multiple hypotheses, updating as evidence changes. Treat the public as adults capable of handling ambiguity. Because they can. Most people understand that science is a process, that answers evolve that we do not yet know, is a perfectly acceptable reaction. Bi-Atlas is an anomaly in a stack. It is important, it is fascinating, but it is not evidence of anything. It is a data point, a mystery, an opportunity to learn, and whether ultimately it is a strange natural comet, or something we have never seen before. The process of studying it, testing hypotheses, ruling out explanations is valuable. That process is science, and science, when done honestly, is one of humanity's greatest achievements, even especially when it is struggling with things it does not yet understand. Part 15. Final reflection. So here we are. Thousands of words deep into the mystery of Bi-Atlas, an interstellar comet pouring water into space where water should not flow, glowing blue 6 with nickel and cyanide flickering on and off, like something intentional carrying chemical reactions from another star system, perhaps another era of galactic history.